Hi everyone, welcome to Random Thoughts with Alex. Einstein's theory of relativity doesn't need an introduction. Both the special theory and the general theory of relativity have been confirmed by measurements with great accuracy. As a mathematical model, we know that relativity is correct with great accuracy. But how certain are we of relativity as a physical model? Well, you might ask, what's the alternative? Is there an alternative? You might be surprised to know that, yes, there is an alternative to special relativity. In fact, there has always been an alternative ever since Einstein published his ideas in 1905. It's known as the Lorentz-ether theory. Yes, it is a theory that involves an ether, and yes, it predicts the same observations also predicted by Einstein. The theory is named after Hendrik Lorentz, a Dutch physicist and contemporary of Einstein, the same person behind the Lorentz transformation and the Lorentz contraction. In this video, I will give an outline of the Lorentz-ether theory as far as I've been able to develop it for myself. I will create separate videos with technical details of the theory. I will start with the principles of the Lorentz-ether theory as I see them, as well as the methods to develop them. Then I will say a few words about every step of the development and its results. This is how I developed the theory, and it may deviate from how others approach it. First of all, the Lorentz-ether theory must follow the equation E equals mc squared. Because we don't adopt the Minkowski space, we can use this equation both for objects at rest and for objects in motion. This will lead to the concept of relativistic mass. Second, the Lorentz-ether theory must follow the principle of relativity, but as an emergent phenomenon, not as a fundamental principle. For instance, when you measure the speed of light in vacuum, you always get the same result, but that tells us more about the properties of our measurement devices than it tells us about light. Third, in the Lorentz-ether theory, space and time are absolute and Galilean. That means there is an absolute standard of rest, there is an absolute time that can be measured with clocks at rest, at least in principle, and velocities are additive in absolute space and time the same way they are in Newtonian mechanics, even at relativistic speeds. In absolute space and time, there is an absolute concept of simultaneity, but we can never observe that. We can only observe an apparent simultaneity the way it was defined by Einstein. This apparent simultaneity will be probed with the thought experiments of Einstein's original theory. This will lead to the Lorentz contraction and to time dilation. At this point, we can only understand that they exist and how they behave, but not yet why. To understand why, we need to investigate how the principle of relativity affects electrostatic phenomena. We will find a result that can also be obtained from Maxwell's equations. Then, with a little bit of quantum mechanics, we can actually derive the Lorentz contraction as a quantum mechanical effect. Applying this to clocks of various kinds shows us that time dilation is just a slowing down of all objects as a result of its electrodynamic properties, not some fundamental slowing down of time. Now, let's take a closer look at each of these steps in the development. First of all, Let's start with the equation E equals mc squared. It tells us that if we add energy to an object, we increase its mass. Mechanically, we add energy by applying a force on it across a certain distance. dE equals F times dx, where d represents an infinitely small change. That force will accelerate the object. In Newtonian mechanics, that acceleration would follow the equation F equals m times a, where F is the force and m is the mass and a is the acceleration. This is Newton's second law. But that assumes that the mass is constant, which is no longer the case when E equals mc squared. Instead, we have to replace it with a law stating that the force equals the change of mass times velocity per unit time. In equation form, F equals d over dt of m times v. Again, d represents an infinitely small change. M times v is also known as the momentum, sometimes indicated with the letter p. The equation then becomes F equals dp over dt. Putting all of this together and applying some calculus, we can prove the following equation from the above. M equals m naught divided by the square root of 1 minus v squared over c squared. In this equation, we call m the relativistic mass. M naught is the mass of the object at rest. We call it the rest mass of the object. This is also the inertial mass that we observe when we move an object in a circle. That means when the force is perpendicular to the direction of the motion of the object. We call that the transverse inertial mass of the object, mt. Because the object moves at a constant speed, although not in a constant direction, the mass is constant and Newton's second law works as usual. But if we accelerate a mass in a straight line, then there is more change of the momentum because both the mass and the velocity are increasing. As a result, the mass will seem heavier than it really is. We call this apparent mass the longitudinal mass. It is ml equals m naught divided by 1 minus v squared over c squared to the power of 3 over 2. This is the first result of the Lorentz-ether theory. The difference between longitudinal mass and transverse mass will be important later on. The second step involves measurements of the speed of light. Every such method is a variant of the following. We send a beam of light to a distant mirror and we measure how long it takes for the light to come back. We measure the distance between the source and the mirror with a ruler and calculate the overall average speed of light from that information. We do this for a system at rest and for the same system in motion. The light travels a longer path in the system in motion. We know from experience that this measurement always gives the same result regardless of the motion of the system as a whole and regardless of the orientation of the system relative to its motion. In absolute space and time, the time needed for the light to travel the distance back and forth is longer when the system is in motion, and in the absence of Lorentz contraction, we would expect the time to depend on the orientation of the system as well. To always get the same result, moving objects must undergo Lorentz contraction in the direction of the motion. moving objects must also undergo time dilation. The Lorentz contraction is as follows. L prime, that means the length of the moving object, equals L, that means the length of the same object at rest, times the square root of 1 minus v squared over c squared. This is only true in the direction of motion. In the directions perpendicular to the motion, there is no change. The time dilation is as follows. T prime, that means the time experienced by a moving object, equals t, that means the time experienced by the object at rest, times the square root of 1 minus v squared over c squared. At this point, we do not yet know why this happens, but we do know that it does happen. This is the second result of the Lorentz-ether theory. At this point, the viewer may have an objection. Assume that an observer at rest and a moving observer each have a ruler. According to the principle of relativity, the observer at rest must see the ruler of the moving observer as shorter than their own ruler. But the moving observer must see the ruler of the stationary observer as shorter than their own ruler, in spite of the fact that their own ruler is objectively the shorter one. How is this possible? It is possible because the mover observer will use the apparent simultaneity of the alignment of the rulers to determine which ruler is the shorter one. In doing so, he or she will check the alignment of the back ends of the rulers first and the alignment of the front ends later, all the while thinking that they are checking both alignments at the same time. That way, their ruler will seem longer when it is actually shorter. Likewise, a moving observer will think that a clock at rest is slower than their own clock when in fact it ticks faster. When we apply the principle of relativity to the electric and gravitational forces, we find that they must be weaker between two moving objects than between two stationary objects. We can speculate that this is because the photons and gravitons between them must move longer distances to interact with the two objects. For the electric force, the effect also follows from the Maxwell equations. In particular, epsilon prime naught, the permittivity of space for a moving object, equals epsilon naught divided by the square root of 1 minus v squared over c squared, or equal to epsilon naught divided by 1 minus v squared over c squared, depending on the orientation, where epsilon naught is the permittivity of space for an object at rest. Now we are finally in a position to calculate the Lorentz contraction from first principles. We do so using quantum mechanics. We don't need relativistic quantum mechanics, we can just use the Schrödinger equation. One of the consequences of the Schrödinger equation is the Bohr radius. The Bohr radius is a measure of the radius of the hydrogen atom. Every molecular size can be expressed in terms of the Bohr radius. In other words, if the Bohr radius changes in a certain direction in certain circumstances, then every molecular size changes by the same proportion in that direction. When we calculate the Bohr radius of a moving object using the relativistic inertial mass and a reduced inertial force, two things we obtained independently of quantum mechanics, then we find that the Bohr radius predicts the Lorentz contraction. And it predicts the contraction in the direction of the motion and not in the perpendicular direction, which is exactly how actual objects behave. In other words, every material must experience Lorentz contraction on a molecular scale as the result of its increasing mass and the decreasing electrical force. This is where the difference between the transverse mass and the longitudinal mass is important. Without this distinction, it would be impossible to predict the Lorentz contraction in one direction and not in the others. Time dilation follows directly from the combination of the reduced force and the increased mass as well, simply by, for instance, the oscillation of a mass on a spring. When we do the calculation in different directions, we always find the same result, as should be the case. In essence, all oscillations slow down due to the balance of the reduced force and the increased mass, not due to some mysterious change in the nature of time. That, in a nutshell, is the Lorentz-ether theory, or at least the version that I was able to come up with. This is how it makes sense to me. I will post more technical videos with calculation details. The details are also in a document that I will link in the description. I hope you like this video. If you do, please like and subscribe, and I will see you in the next video.